Emma, and I like ham radio. Today we're going to learn about circuits.
So Emma, we've mentioned a few words in our previous videos that we probably need to explain a bit more. I know that you know what they mean, but not everyone does.
Which words?
Well, one word is circuit. We first mentioned it in our video about voltage. Remember the thing we measured voltage on that wasn't a battery?
Oh yeah, snap circuits.
Yeah, there's that word again, circuit. We should explain it a bit more. We'll talk about how antennas seem like they break the rules a bit.
Break the rules?
Yeah, they don't really break the rules, but let's talk about what the rules are first.
Okay.
Let's start with what the word means. The dictionary definition that I like is a circular journey or one beginning and ending in the same place. Where does that journey begin, Emma?
The battery.
Yeah. Circuits start with a power source. Many times that's a battery, but it could also be an outlet on the wall, or a generator, or a solar panel. If you're going on a journey, you need somewhere to go, right? What are the roads in the electrical world?
Wires.
Yep, electricity travels on wires. It also needs some stops along the way. What's your favorite thing for electricity to travel through?
LEDs.
Who doesn't like blinky lights? Alright, if I use a piece of wire to connect a battery to an LED, would that work?
No, you have to connect it back to the battery.
Yeah, you're right. Our definition of circuit talked about beginning and ending at the same place. In our example, that same place is the power source, the battery. Why does that have to connect back to the battery?
So that the electrons can flow.
Yeah, you can think of a power source like a battery, sort of an electron pump. It takes electrons from one end and pushes them out the other. If there are no electrons to grab on one end, then it's like a pump with no water. So we basically recycle the electrons.
The electricity flows out the positive end, around the circuit, then back to the negative end.
Okay, now here's the tough question. Ready? If a circuit has to be connected in a loop, how does an antenna work? It's just a long piece of metal sticking out into space.
I don't know.
Okay, obviously this is a complex topic, but I'll give you the simple way that I think about it in my head and see if that helps. Imagine if you have a piece of empty string and you start stringing beads on it. Eventually you'll have to stop. Why?
Because the string will fill up with beads and there would be no more space.
Right. One thing I could do is to start taking beads off the other end, right? I could keep taking beads off the far end, bringing them around and putting them on the near end.
Then you'd be a battery.
Yep, that's basically how a battery works. But what if I couldn't reach the other end?
Then you couldn't put more beads on.
Sure, but I could take beads off.
Oh yeah.
Yeah, I could start taking beads off until the string was empty again, and then I could start putting beads back on. Hey, wait a minute. If the beads go on the string and off the string, they would be changing direction a lot. That sounds like something else we've talked about.
Alternating current.
You got it. A radio pushes and pulls electrons on the antenna back and forth to create a wave. So even though the end of the antenna isn't connected, there are still electrons moving. We'll be talking more about antennas and waves in future videos. So for now, we'll go back to the regular circuits that are connected in a loop. In our video about current, we talked about having to connect the meter in a certain way. Do you remember the word?
In series.
Yeah. In series means that you're connecting parts together. They're connected one after next. So the electricity flows to one part, then the next, and then the next. And you can't get to another part without going through the part before it.
Kind of like the beads.
Exactly. There's another way to connect components together. Do you remember what that's called?
In parallel, like when we measured voltage.
Yeah, so parallel is different than serial in that there are branches in the wires so that the electricity has more than one path to take. When electricity comes to a fork in the road, it goes both directions, like water in a garden hose splitter. Unlike serial circuits, parallel circuits have multiple paths through the circuit.
That sounds confusing to figure out.
Sometimes it can be. But parallel circuits can also have some benefits. Ever have a string of Christmas lights where one bulb burns out? What happens?
They all go out.
Yeah, a lot of Christmas lights are wired in series. So if a bulb burns out, it breaks the circuit and no current flows to the ones before it or the ones after. Some fancier Christmas lights are wired in parallel. So that if one burns out, the electricity can still go around the burnt out bulb and get to the rest.
Then only one goes out.
Yeah. Most electronics use a mix of serial and parallel connections depending on the design. For example, when you connect an LED to a battery, what else do you need to keep the LED from burning up?
A resistor.
Yeah. In that case, you need to wire them in series because you need to make sure the current goes through the resistor to protect the LED. What would happen if you wired it in parallel?
Poof! I accidentally did that once, and suddenly my yellow LED wouldn't work.
Yeah, the current could just bypass the resistor to go through the LED, and bye-bye LED. Now is a great time to talk about how voltage and current change when flowing through both of these types of circuits. Let's talk about series first. Since we're talking about your LED and resistor circuit, Emma, what color of LED is your favorite?
Blue.
Okay, imagine you have a battery, a blue LED, and a 50 ohm resistor all connected in series. In a series circuit, the current would be the same everywhere in the circuit.
Everywhere?
Well, remember our string of beads? Can you put them on faster than you can take them off?
Only until the string is full, then you can put on as many beads as you take off.
Right. So if there's a resistor in the circuit and it's resisting the current flow, it affects the whole circuit. Another way you can think about it is like a garden hose. If you put a kink in the middle of the hose, the water slows down or stops at both ends.
Oh, yeah.
Okay, so we know what happens to the current. What about the voltage in a series circuit? Is it the same throughout, like current?
No, the components can change it. They steal some, like we talked about in our voltage video.
Wow, good memory. You're right. In a series circuit, the voltage can change depending on what parts you have connected. If you use the garden hose with the kink in it example again, the pressure of the water is a lot greater before the kink and a lot lower after it.
The kink in the hose is like a resistor.
Yeah, they both resist the current, don't they? Okay, so that's a serial circuit. But what about a parallel circuit? How does the current change in a parallel circuit? Is it the same like a series circuit?
No, it changes depending on what components are connected.
Right. So back to our garden hose. If you put a splitter on the hose and connected a sprinkler to one side and a spray nozzle to the other, what would happen?
Well, the sprinkler would just go until you squeeze the handle of the sprayer.
What would happen to the sprinkler when you squeeze the handle on the spray nozzle?
It wouldn't go as far because some of the water would be going out of the sprayer.
Yeah,
Because
when the nozzle is closed, all the water would be going to the sprinkler. When you open the nozzle, the water would be divided between the sprinkler and the nozzle. It's pretty much the same for electricity when parts are connected in parallel. The current is divided between them, depending on how much current can pass through each part. Okay, now what about voltage? When it comes to parts connected in parallel, does it change like it does in a serial circuit?
No, the voltage stays the same.
Good job, you're right. The current gets divided between the components, but voltage, or the pressure, stays the same. When you're comparing it to what we call water pressure, it might not seem that way, but that's because most people judge water pressure by the amount of water coming out of the spout. But that's really current. In some houses, if you're in the shower and someone else flushes the toilet, the water can get really hot or cold. That's not because the pump changed how much pressure it's providing. It's still pumping with the same pressure as always. It's because the current is being divided between two places, the shower and the toilet. Okay, now that we talked about circuits, it sounds like we should get out the snap circuits.
Let's get hands on!
Okay, we got out Emma's snap circuits to learn about circuits. So she has built a starter circuit here. You want to explain it?
So, this is the battery. And then that's where you get the voltage from.
Right.
It goes, there's a little plus sign there. I don't know if you can see it. Yeah, you can. And then it goes through the switch, which is off right now. So look at this little diagram. Think of it right now. This little diagram would be in the off position because the circuit is open. But then when it turns on, just imagine that closing. And then this is our resistor that it resists the flow, kind of like the turnstiles in the Electric Rock concert. And then this is our little indicator. It's called an LED, a light emitting diode. So we're just using it for a little indicator so you can see that power is on. And then back to the battery and around and around.
And that's our circuit, right? Yep. It leaves from one spot and it comes around and returns to the battery, right? So let's turn it on.
All right.
Okay. Yay! Now let's make a series circuit with 2 lights in it. Can you do that?
Yeah, I can. Here, let me grab it out of my little kit here. Okay, let's see. All right. Actually, for this circuit, we actually don't need a resistor because this will be taking some of the power. It won't actually run if there's
the light acts as a resistor, doesn't it?
So we'll just take that out of the circuit, put it in our little kit there. Alright, we'll stick this here, like that, and how big is that? Okay, grab this out of here. Takes a second.
Yep. All right.
Gotta get all the parts out of my box.
So what do you have now? We took the resistor out.
So no resistor, but this is still the batteries, still the switch. And then we added a lamp, which is close to an LED, but it takes more voltage, which that will be important to know later. And then our LED, again, our indicator. This is also an indicator too, so they could probably be used interchangeably, especially with snap circuits. And then this is just a placeholder, so that
it's just a wire going back, right? So let's turn it on and see what happens.
Wait, what?
So
why
did only one light up?
I think I know why. So snap circuits, I'm pretty sure, has a resistor built in with their LED module thing. So I'm pretty sure that is slowing down most of the current going through so that it's enough for this LED. So like if you forget to put the resistor in your circuit for snap circuits, your LED is probably not going to blow out. I haven't tested that yet.
Do you remember how we said that in a series circuit? Remember how we said that throughout the whole circuit the amperage should be the same, right?
Yeah.
But what did we say about the voltage?
The voltage changes.
The voltage changes depending on... So the LED is going to reduce the voltage, and so is this. They're both going to reduce the voltage a little bit.
So it's not enough for the lamp to light.
Right. So what happens if we swap them? Let's put the LED first.
Alrighty, we'll just swap them. They're the same length, so that's the nice thing with snap circuits. They're all the same length. And this one doesn't matter which way it goes, so that's not the reason why.
Yeah. So let's turn it on. Okay.
Still doesn't work. Still doesn't work.
So what would we do if we wanted this to work?
Should we put it in parallel?
Yeah, let's do it in parallel.
Okay. Alright, we'll pull out our stuff for parallel here.
Just do a 3 here, maybe?
The reason why we're saying these little numbers is because these wires come in different lengths. Don't know if you like that.
You can see.
So...
Here, I'll lift it up.
Yeah, they come in different lengths, so that's the number of snaps they have on them. So a 3 is 3 snaps, and the same. All the components are the same size as a 3.
Yeah, it makes it really nice. And we're using snap circuits because it's a lot easier to see.
Just snap.
Well, it's bigger so that you can see it on camera. Because if we were using a real LED,
because it'd be this big instead of this big.
Yeah, and there's just little wires coming off of it, and things like the wires will be a little harder to see. This makes it a lot easier to see because it's bigger.
Plus, it also looks like a schematic, which is like the diagram. Because it's got the symbol here, and it doesn't have a symbol here, but it...
Yeah.
Yeah.
All right, let's turn it on and see.
Yay! Woohoo!
They both light. Now, if you remember...
I'll turn it off here.
You can leave it on.
Okay.
It's just batteries.
Yeah.
So if you remember, now where is the voltage flowing?
Both ways.
It's yes, right. It's coming out here. And remember how we said that it kind of splits and it goes both ways through.
So you can actually prove that it's splitting, right?
Yeah, you want to see what the voltage is?
Okay, you probably should have it on the voltage setting.
Yeah, let's switch it to voltage. There we
She
go.
has it on ohms right now. Resistance. Okay, so where would we do it to? This.
Yep.
And this. So that's 240. What about that?
2.4, yeah.
240.
Right, so the voltage in both places is the same. So
yeah, but what's the voltage here?
Yep. Same there.
Yep.
Now in our series circuit, it wouldn't have been the
You
same.
want me to make it again?
We can try it. Yeah, you want?
It's really easy. Since this 3 is the same length as
Yeah.
so then we'll put which one we want to put first?
Doesn't matter.
Okay, because it doesn't work. All right, so we'll turn it on.
Yep. So I'll put your there, and then we'll measure it there. 0.4. Yep. Now what about here?
What's this? Way lower.
That's you have a bad connection there. 2.4. How about here? Let me move it down and see if we.
Well, this is lighting, so we don't have a bad connection here.
Yeah, we have a good connection. It's just that the voltage.
Oh, there we go.
Let me switch it there. So the voltage is dropping quite a bit as it goes through there. Let's actually switch it to here. So 2.5.
2.5, and then this is
A lot less, huh?
0.4
As
or
it goes through
0.04, which is way lower than.
So there's actually a pretty large voltage drop on an LED, especially for the batteries that we have here.
Yeah.
It would be easier to see if it was like 9 volts.
Which I'm pretty sure the part of the reason for the drop, it's not all of the reason, but I'm pretty sure, like I said before, there is probably a resistor in here. So if you forget to stick a resistor in the circuit and you go whoops, it won't go and explode, and you don't have to buy another snap circuit kit.
So what's happening, I believe, is that the voltage, the LED is dropping the voltage so much that it's not enough to light the lamp.
Yeah, you're right.
Let's try it with something else. Let's put a motor in there and see how that works.
All right. We got our little motor here.
The motor shouldn't have as much of a voltage drop, I don't think, as an LED. We'll see.
We gotta make sure. So the motor actually is, you have to make sure that the plus sign goes to the plus sign here. But the lamp doesn't have that. So.
All right, now we got motor and lamp. What happens?
The motor doesn't.
Motor doesn't work, does it?
I don't know if you can see that.
So let's check it out though.
But it didn't turn. Just so you know.
Yeah, it's not turning. So let's check and see. So now what do we have? Now we have 1.6 voltage
What's
there.
here though?
That's going to be 2.4.
Oh.
Okay.
This is going to be 1.6.
So 1.6, and what about right there? And it's dropping down.
Yeah.
Okay, so the voltage is changing.
Yeah.
Because
the
of
poor
that.
motor doesn't get to turn.
Should we see exactly how much voltage it drops? Let's just put it. Let's cross this here.
Yeah. We have our little handy dandy 3 here.
And then check it. Turn it on and check it.
That's bizarre.
There we go.
Ah, there we go.
Here, put it here and put it there. There's 2.4. And it's using almost all of our voltage, isn't it?
Yeah. So that's why I didn't have enough to run, because the lamp takes most of our voltage too. So.
But if we want them both to run, what do? We don't want them to have in series, do we? We want them to be in parallel.
Let me make this We want it to be in parallel. And it just so happens that this motor is not fat enough that it
fits in
hinders
there,
us.
doesn't it?
Yeah. I think it's meant to be that, like that. Ready? Whoa!
Well, they both run, right?
So, I don't know if you can hear it or not, but it's running.
So the voltage is splitting, and so both components are getting the same amount of voltage.
Yeah. So they both have enough to run.
Now there's going to be a different amount of amperage, isn't there?
Yeah.
Should we test that?
Yeah.
Okay.
I'll turn it back on.
So let's switch over to...
You can probably hear it. I don't know.
Let's switch over there, and we're going to have to disconnect something. Let's take the motor out a minute. Well, we're just going to do this.
Motor.
Now we can take our probes and put them in between there. So over here.
Okay.
So from here to there.
Here to where?
From here to there.
Oh. Oh.
See?
Yeah, just a second.
Oh yeah, we're touching the...
Yeah,
Actually, here, let's do it this way. Now you can...
Yeah. Oh, it's because the technically has a conductor. You're on volts.
Yeah,
oh,
there we go.
Not.
There we go. Now
Wow.
there's about 60 milliamps going through that little motor.
Wow.
Okay. Now how many little milliamps are going through the light?
Well, we'll turn it off here while we do this.
Yep.
Oh, look.
Yeah.
If you hear it, it's actually slowing down when I stick this on here. I don't know if you can hear that.
So yeah, we can hear it. So it's about 150 milliamps going through there.
Yeah.
Okay. Now what's happening is these batteries can only put out so many amps.
Yeah.
And so when it's not shared across the motor runs faster because there's more amps going through there.
Because watch. Here, let's just pop this one off. Oh, here. So watch.
Yep.
And you can hear it go doo, which means it's running slower, but it's running faster when I take that off.
So, like, if we were using our water analogy from the lesson, right? So let's say somebody's in the shower, right? And the motor is the shower, and then somebody flushes the toilet, right?
Yeah.
There's only so much. Now, what we said about it though is that the voltage is the same. So these batteries are putting out the same amount of voltage.
Yeah.
It's just that the current changes when it's split between the two.
Yeah. Also, if you touch two parts on here, it's okay because, like, so if I were to do this, it's okay because I've done it before and it just tickles a little bit. So don't be like, it's gonna kill me or anything like that.
Right. It's only 3 volts with these batteries put together.
Yeah, it's not much. So
all right. So yeah, we tested to see how voltage and amperage changes and in the 2 different kinds of circuits.
Yeah.
In which type of circuit is current the same through all components? A. Series. B. Parallel. C. Resonant. And D. Branch.
So we can rule out, based on our lesson, we can rule out resonant and branch because those aren't types of circuits.
Right.
So we're limited to A and B, so series or parallel. I think the answer is series.
You are correct. It's A. What happens to current at the junction of 2 components in series? A. It divides equally between them. B. It's unchanged. C. It divides based on the value of the components. And D. The current is the second component. In the second component is 0.
Oh, let's see. I think it would be.
So we're talking about a series.
And it's current.
Right. And if you remember, so we're talking about, so these components would be right after each other. So we're talking about the current.
Right.
Remember we talked about beads. Remember the beads in the series?
I think it'll be B. It is unchanged.
That's correct. Good job. What is the voltage across each of two components in series with a voltage source? A, the same voltage as the source. B, half the source voltage. C, it's determined by the type and value of the components. And D, twice the source voltage.
Well, I know we can rule out twice the source voltage because...
That would be awesome.
Yeah, it would.
If we could you just connect a component and you get more voltage.
Yeah, that would be really awesome. But it doesn't happen that way. So
Nope.
I would say A, the same voltage. Oh, wait, no. Sorry. B, half the source
think?
voltage.
Depends. Well, so let's think about that a minute. Imagine that you had a resistor connected in there.
Is it C?
It's going to be determined by the type and value of the components. Is that your answer?
Yes.
You got it. It's C. So it might be half the source voltage, but that would depend on...
If you had like two LEDs, if they were the same, then it would be half.
Yeah, possibly. It all depends on how much... Remember how we said the components, they steal some?
Right.
Kind of depends on how much voltage they steal. So it could be half the source voltage, but probably not.
Yeah.
In which type of circuit is voltage the same across all components? A, series. B, parallel. C, resonant. And D, branch.
Again, resonant and branch aren't types of circuits. So again, we're limited to A and B. So if you think about it, I think it would be parallel because it's like a ladder. Each rung of the ladder gets the same amount of voltage.
All right, let's check. You're correct. It's B. What happens to current at the junction of two components in parallel? A, it divides between them dependent on the value of the components. B, it's the same in both components. C, its value doubles. Or D, its value is halved.
Well, it'd be great if it was C, but I don't think it is. I'm gonna guess B.
It's the same in both components. So let's think about this. Remember, let's read it carefully. What happens to current at the junction of two components in parallel? So we're talking about parallel,
Yep.
and we're talking about current, not voltage.
Right. So would it be A?
Correct. It divides between them dependent on the value of the components. So think of it like, imagine you got a bunch of kids that are walking down a path. And the path, let's say they're part of a school class. Well, you get to a fork in the road. So some of them go left, some of them go right. Now, depending on what they encounter, so maybe the ones that went to the left, they get to a big muddy swamp, right? And the people that go to the right, they get to a nice smooth sidewalk. Which ones are going to go faster?
The smooth sidewalk.
Right. So it depends on what the value of the components are. So if the swamp is like a resistor, the flow of the kids through that path is going to be different. What's the voltage across each of two components in parallel with a voltage source? So this is very similar to the previous question. A, it's determined by the type and value of the components. B, half the source voltage. C, twice the source voltage. And D, the same voltage as the source. So again, let's talk about this one again, right? So
again, if it were C, it'd be awesome because then you could just double it.
Just have magic source of voltage.
Yep.
But it's voltage in this case, and it's in parallel. So remember what we talked about with the pump in the house?
Yeah.
The voltage is the pressure, kind of, isn't it?
Yeah.
So what would you say it is?
I would say A.
A is it's determined by the type and value of the components. Actually, that would be true for current. Right? That's the answer for current.
Is it D?
It would be D, the same voltage as the source. Good job.